Okay, so let's continue with the session. The next talk is actually joined with the Dynamical Systems session. The speaker is Bowen. He's a full professor at the University of Texas, Austin. I think he also did his PhD there.
Yes.
Yes, okay, good. And, well, he has done some groundbreaking work on Sofic entropy, and he's going to tell us about it. The title of the talk is A Brief Introduction to Sofic Entropy Theory.
Okay. First, I'd like to thank the organizers for giving me this wonderful opportunity. Of course, it's a great honor to speak at the ICM. And it's been a pleasure to be here in Rio. It's a first time for me. Okay, so my talk is going to be about Sofic entropy theory. This is an entropy theory that I introduced in 2008. It's an entropy theory for countable groups acting either on compact spaces by homeomorphisms or so that's the topological Sofic entropy theory. And there's also a measure theoretic counterpart for countable groups acting on probability spaces by measure preserving transformations. So soon after I introduced this theory, David Kerr and Hanfeng Li improved upon it. So I introduced it only in the measure theoretic setting. They extended it to the topological setting and removed some unnecessary hypotheses that I had. So my talk is going to be a gentle introduction to all of these things, mostly for non-experts. And I'll get to newer developments at the very end. So to start, I would like to start with entropy theory for actions of the integers. Actually, here's just a very brief review. Classical entropy theory is concerned with systems that evolve in time, where time is represented here by the integers. And so a typical setup is that we have a homeomorphism of a compact metrizable space representing time. And the topological entropy is the infimum over all epsilon of the exponential growth rate of the number of partial orbits that can be distinguished up to epsilon. Well, at scale epsilon. So here's a precise version. So this is just a bit of review. This definition is due to Rufus Bowen, by the way, who is no relationship to myself. Okay, so a length n partial orbit just means that it is an n-tuple, x, tx, t squared x, etc. So here is just a picture to have in mind. So the way I like to think of a partial orbit is that we have a part of the number line, and we're just mapping that into x. Okay, so let's fix a metric. It turns out that the topological entropy does not depend on the choice of metric, but it's convenient to have a metric. Then the rho infinity distance between two partial orbits is just the maximum distance between their ith iterates. And so the entropy is defined in this following way. We look at all length n partial orbits. Now, typically, there's infinitely many, so we can't just count them. That won't be helpful. So what we do is we take the minimum cardinality of a collection of partial orbits that epsilon covers the space of partial orbits. So this is the epsilon covering number. And we look at the exponential rate of growth of this epsilon covering number. And then we send epsilon down to 0. Okay. Now, these are some main results. This is all very standard, by the way. This is like And Dynamics 101. Okay, so if we have one system that embeds into another, so if X can be realized as a subset of Y, so that T is just the restriction of S to X, then the entropy is monotone. And that's an easy exercise. In particular, entropy doesn't depend on the choice of metric because of any two metrics will be uniformly equivalent. And so it's a topological conjugacy invariant. And it's also monotone under factors. So if we have a transformation from X to X, and we also have a map from X to Y, which converts T to some other map, some other homeomorphism S, then the entropy of the upstairs transformation bounds the entropy of the downstairs one. And this is very easy to see because you see if we have any partial orbit in Y, we can lift it to a partial orbit in X. And so any witness to the entropy of this downstairs transformation lifts to a witness to the entropy of the upstairs one. Okay. So topological entropy was defined earlier in a different way, just to give credit where credit is due, by these three people. Okay, but what happens if we replace the integers with the free group of rank 2? Before getting to the free group of rank 2, by the way, you might think of replacing z with z to the d, and that turns out to be easy to handle. In fact, any amenable group turns out that one can generalize entropy theory in a fairly straightforward way. But when you get to a non-amenable group, such as the free group of rank 2, unusual phenomena occur. And this unusual phenomena is well illustrated. So just to have a picture in mind, by the way, this is the rank 2 free group, the Cayley graph of it. So, so the vertices represent elements of the group, and there is an edge from one vertex to another if you can get from one to another by right multiplication by a generator. Okay. I'm going to give you a funny example pretty soon, but I need to just explain a class of important examples first. So if K is a Borel space, and if you like, just think of K as being a finite set. That's already a very interesting case. Then the full K shift is the following. So we look at all functions from our group to K. You could think of these as colorings of the group by elements of K. And the group acts on this space of functions by just shifting the input. So it's like just translating the input. So if K has a topology, then this action is continuous. And the full shift has entropy log of K when the acting group is the integers, or in fact any amenable group. And so in particular, what we get out of this is that the 2 shift, when we just have 2 elements, it cannot map onto the 4 shift. That would increase entropy. The 2 shift is like saying, okay, we have 1 bit of information per group element, and the 4 shift is saying we have 4 bits or 2 bits of information rather, and we can't increase information by putting on some sunglasses and forgetting something. So if we're going to map one thing onto another, we're losing information, and so entropy should go down. Well, or it could stay the same, but it can't increase. Okay, but Ornstein and Weiss showed in 1987 that in the case of the free group, in fact, the 2 shift factors onto the 4 shift. But this doesn't contradict anything because at this point in time, there's no entropy theory. And in fact, the map is very, very simple. I'll explain it in a moment. Actually, let me just explain it right now. Here it is in pictures. You see, you have zeros and ones on all the vertices. You take this vertex, you add it to the digit, or the binary digit to the north of it, and you add that mod 2, and you place it here. Then you take this same one and you add it to the one east of it, and you put that here. Let me explain this map a little bit. What you see is that it's just the co-boundary operator, basically, right? If we just add two elements that span an edge, if we just put the value of adding these two elements together at the edge, that would be called the co-boundary. And so the tree is simply connected, and so its cohomology is trivial. And this tells you that this map is in fact surjective. And it's clearly equivariant. We're doing the same thing everywhere. And in fact, it's a 2-to-1 map. The kernel of this map, it is a homomorphism of compact abelian groups. The kernel consists of the constants, all zeros or all ones. There's just two elements of the kernel. It's a 2-to-1 map. So just to recap, it's surjective, it's shift equivariant, it's 2-to-1, continuous. So it's a multi-purpose counterexample. And they asked, well, these two, the 2-shift and the 4-shift, they can't be topologically conjugate because one has 2 fixed points and the other one has 4. But those fixed points are just a set of measure 0. So maybe if we got rid of measure 0 sets and we just looked at measurable isomorphisms, maybe they're isomorphic. And so this remained an open problem until 2008, when just a more recent result by Laurent Bartholdi is that, in fact, this phenomena extends to any non-amenable group. If you have any non-amenable group, there are integers m strictly less than n, and shift equivariant continuous surjective map. Okay, so before getting to Sofic entropy theory, I'd like to go back to the integers, because it will be easier to understand it from that point of view first. So we're just going to reformulate or rethink the case of entropy for the integers. Okay. So we will look at pseudo partial orbits. And let me show you a picture, and then I'll explain the algebra. So we just take this part of the number line, as we did before, and we map it in some way into our space X. But this time, we don't require that we don't require that X1 is the transformation applied to X0. Instead, it just has to be close, and it just has to be close in an average L1 sense. Okay, so this is the precise version. We look at the distance between Txi and xi plus 1. And we look at the average L1 distance. And if that's less than delta, we call that a delta, n delta pseudo-orbit. Well, it's an exercise to prove that counting pseudo-orbits instead of partial orbits is an alternative way to get entropy. The one-line proof is that you can use Markov's inequality to show that any pseudo-orbit is approximately close to a union of just a few partial orbits. So just a few means a small number relative to n, to the length. And so once you have a pseudo-orbit, you in fact have the usual kinds of partial orbits nearby. And so once you have a witness to the entropy for using this definition, you have a witness using the previous definition. Okay, let me just kind of just keep thinking a little bit, just to see how the progression of ideas goes. A periodic orbit is something that's well studied in dynamics. And so it just means that we have an n-tuple where Tn of x is x. So we just think of it, I like to think of it as just a map from the n cycle, the discrete n cycle, into x, which is equivariant. Okay, now the exponential rate of growth of the number of periodic points does not give us entropy. It's a lower bound on entropy, but it's not entropy in general. But what we can do, we're thinking about pseudo-orbits and we're thinking about periodic orbits. We can look at pseudo-periodic orbits. So we just need to tweak the concept of a periodic orbit. So all it is we have an n-tuple. And this time we sum from I equals 1 to n, and we take the indices mod n. It's a very small change, okay? I'm not, so we just have a map from the n cycle into our space, and it's approximately equivariant in an average L1 sense. Now this is, of course, we have the same theorem here with pseudo-periodic orbits in place of pseudo-orbits, because this extra little bit that we're counting is on order of 1 over n, so it doesn't really contribute anything. The reason for pointing this out is that now we have an idea which generalizes to arbitrary groups. You see, if we have an arbitrary countable group, we can make sense of a periodic orbit. That's just a finite orbit. And now we can also make sense of approximate equivariance in an L1 sense. So just a bit of terminology. If you're interested and you're looking at the literature, these pseudo-periodic orbits are sometimes called microstates by inspiration with statistical physics, or good maps or Sofic models. Okay, now let's suppose that we have a countable group, and this time I'm just taking any arbitrary countable group, just for the moment. And we have an action by homeomorphisms, and we want to make sense of what is the entropy. So here is a preliminary definition. We will need to make a few minor changes later on. So first, let's say that we have an action on a finite set, and we have a map from that finite set into X, and it's approximately equivariant in this L1 sense. So this sense, we have to choose some finite subset of the group in order to make this meaningful. So approximate equivariance depends on a choice of delta, error tolerance, and a finite set. Okay. So we call that a sigma delta F pseudo-periodic orbit. We need more and more parameters to say what we're talking about, but okay, that's how it goes. This is just a picture, we have the free group here. It's acting on a finite set, the vertices of a cube. So for example, the red generator just takes this vertex to that vertex. That's what it means. Okay, and then we might have some approximately equivariant map into X. Okay, now suppose that we fix some sequence of actions on finite sets. And for the moment, this is an arbitrary sequence. Later on, we'll impose conditions. So we define the Sofic entropy to be the exponential rate of growth of the epsilon covering numbers of the pseudo-periodic orbits. We have to take here the infimum over our parameters and then the supremum at the end. Okay. So here are some main results. If we have an action that embeds into another action, then entropy is monotone. This is not hard to prove. It's because any pseudo-periodic orbit for this action is a pseudo-periodic orbit for the larger action automatically. So we do get a topological conjugacy invariant. And, okay, the entropy of the full shift is still log K. This is not a difficult computation. It's just that, well, I should be a little bit careful here. It depends on the choice of sequence of finite actions. But if you take a nice enough sequence, and I'll say what that means in a moment, then this is true. And that's just because you just label the vertices of your finite set by elements in K arbitrarily in order to get good maps. I'll say a little more about that later on. In the amenable case, this just agrees with classical entropy. And that's because any action of an amenable group on a finite set can be decomposed so that it looks like Fulner sets. And then it just agrees with the classical definition. Okay, let me give you two examples just to get a good feeling for this. The boring example is when these finite sets that we are using to model our action are just trivial, to just 1 point. That's a really bad choice. In this case, this entropy is just the logarithm of the number of fixed points. And that's not what we mean by entropy, so we're going to require that our actions witness the whole group, so we can reconstruct our group from the actions. And what we mean is that if we take any non-trivial element of the group, then the fraction of vertices which is moved by that element tends to 1. So this is looking more and more like the action of the group on itself by left translation. And that's the idea to have in mind. If this assumption holds, then we say that this sequence of actions is a Sofic approximation. Okay, here's a more unusual example, maybe a more interesting example. In order to explain this example, I need a little bit of visual notation. So let's say that I have an action on a finite set, and then I just form the following graph. So if my finite set is 0, 1, 2, 3, then I put an arrow whenever a red generator takes one element to another. Then I put an arrow connecting them. Okay, so for example, in this example, the red generator just is addition mod 1, and the blue generator swaps 0 and 3 and swaps 1 and 2. Okay, so let's compute the Sofic entropy of a very simple action, this action. So we just have 2 elements, 0 and 1, that's x. And my group just swaps these 2. Okay, now suppose that my models, my Sofic, my actions on finite sets, which I've given, and which are supposed to model the action of my group on itself by translation, suppose that each one of those gives me a bipartite graph. Well, then there exists a pseudo-periodic orbit. In fact, there exist periodic orbits, right? I can just map 0 to 0, 1 to 1. And that takes red arrows to red arrows, blue arrows to blue arrows. It's okay. And in fact, there's only 2 periodic orbits, and the number of almost or pseudo-periodic orbits is going to be growing very, very slowly, and you can check that the entropy is 0. On the other hand, if we have one pseudo-periodic orbit, if delta is kind of small, and we just take this for our finite set, the set of generators, then we have an almost bipartition of our Sofic model. And so in particular, if the graphs of our Sofic models are not almost bipartite, then there are no pseudo-periodic orbits at all, and log of 0 is minus infinity. So the entropy is minus infinity. Now, this really does happen. The free group, if you just choose actions at random on finite sets, then with probability 1, there won't be any almost bipartitions. And you will have a Sofic approximation. Points will be moved. So the Sofic entropy can depend on this choice of Sofic approximation. Just to remind you, a Sofic approximation, right, is a sequence of finite graphs or finite sets on which the group acts. And it's approximating the action on itself by left translation. Okay, so let me, let's see. Okay, so here's another example. I mean, here's the Ornstein-Weiss example just seen now from this point of view. The problem with the Ornstein-Weiss example, why entropy increases, is because if we have a pseudo-periodic orbit for the factor, it doesn't necessarily lift. Now, this can't happen with an amenable group, because for an amenable group, any pseudo-periodic orbit is going to be close to a bunch of Fulner sets, and then you can lift those up. So because those are just partial orbits. I'm sorry. Like for Z, for example, if the group is Z, any pseudo-periodic orbit is close to a partial orbit, and you can lift up partial orbits. This is related to some, this has a cohomological interpretation. The reason why is because it turns out that if you have a pseudo-partial orbit, well, you can define a map on the edges in this way. And this map on the edges, the original map can be lifted if and only if this map on the edges is a co-boundary, or is at least close to a co-boundary. And so what you get is that the increase in entropy, which was log 2, is exactly the exponential rate of growth of the cohomology of these graphs. Here's just a quick aside. This Ornstein-Weiss example has been generalized to other groups by Gaborio and Seward. Basically, you just look at, you take some like finite group, for example, K, and you look at K to the gamma modulo K, where K embeds in K to the gamma as the constants. And the increase in entropy is related to the first L2 Betti number, or to the cost of the group. So these are cohomological invariants. Okay, so let me give you a quick application of Sofic entropy theory before getting to the measure theoretic case. In 1973, Gottschalk conjectured the following. If we have a finite set, and we have a map from K to the gamma to K to the gamma, which is equivariant and continuous, if it's injective, then it has to be surjective. In a way, this is kind of generalizing a very fundamental property of finite sets. If I have a finite set, then a map from it back to itself, if it's injective, it has to be surjective. That's a basic finiteness property. So he conjectured that this would be true for these kinds of maps, which are called cellular automata. And Gromov introduced Sofic groups, which I haven't told you what that is yet, but I will. Then the conjecture is true. Okay. So here's the proof. So, okay, so here's the proof. So Sofic groups, by the way, I'll tell you what it is in a moment, but there are groups to which this entropy theory applies. Okay. So the entropy theory, the entropy of this action, of the full shift, is just log of the cardinality of K. So if we have an injective map, well, entropy is a topological conjugacy invariant, so it has to preserve the entropy. The entropy of the image still has to be log of K. But the entropy of any proper subshift is strictly less than log K. And that's easy to see. If you have any finite portion of the group, and if saying that you have a proper subshift means that you have some finite forbidden configuration. And if you have a forbidden configuration somewhere, well, you can imagine packing the group by subsets, which are the domain of this configuration, and then saying, well, we can't, we have some forbidden configuration is going to decrease the number of ways that we can color by an exponential amount. Okay, so this slide should have gone before the other one, but oh well. So it turns out that we don't actually need actions on finite sets. At this point, all of this has been, we've assumed that we have actions on finite sets, but we don't actually need that. All we need is the following. So we need maps from gamma into the symmetric group, which are asymptotically homomorphisms, in the sense that if we fix two elements G and H in gamma, then the fraction of vertices that satisfy, where the homomorphism equation is satisfied, that fraction tends to 1. That's all we need. We still need asymptotic freeness, which is the condition that we saw previously. So we say that a sequence is called a Sofic approximation if it satisfies these two conditions. And gamma is Sofic if it has a Sofic approximation. So these groups and this property was studied by Gromov, but he didn't really give it a name. So Benji Weiss gave it a name in 2000 and made it more accessible to a broader audience. So by the way, I guess it may seem kind of strange, these conditions. So here's a picture, just to get in mind, If you have z squared, and if you have an action on a finite set, you may think of that as a finite torus, discrete torus, pictorially. But if you have a Sofic approximation, what's that? Well, you can do the same thing. You can say, well, we'll put vertices down, and then we'll say, if we have a red generator, if it takes one vertex to another, we'll put an edge, just as we did before. But this time we might have some mistakes. So we might have some small percentage of weird vertices where the locally doesn't look like z squared. That's what it means. Okay, so which groups are Sofic? Amenable groups are Sofic. It's a very large class of groups already. And residually finite groups. Malchev proved that all finitely generated all finitely generated linear groups are residually finite. And it's easy to show that Soficity is preserved under direct unions. So a group is Sofic if and only if all of its finitely generated subgroups are Sofic. So in fact, all linear groups are Sofic. And this class of Sofic groups is closed under many operations like subgroups and direct limits, inverse limits. Some of these are kind of exercises. Some of these results are very easy. Some of them are hard. Proving that free groups with amenable amalgamation is a more difficult result that was proven by these three groups of co-authors independently. Wreath products was done recently by Ben Hayes and Andrew Sal. Also, Sofic groups, they satisfy many interesting properties that are conjectured to hold for all groups. So Gottschalk's surjunctivity conjecture is one of these. Kahn's embedding conjecture is one. So That's that the group von Neumann algebra embeds into ultra product of hyperfinite two-one factors. The determinant conjecture, which is a conjecture in L2 invariance, and Kaplansky's direct finiteness conjecture, which is a conjecture about the group ring. Group rings over finite fields. And also there was a talk, Andreas Thom's talk, he mentioned another conjecture which is just now slipping my mind, sorry. But you should ask Andreas. The Curvaire conjecture, right? Okay. So it's an open problem if every countable group is Sofic. This is, what one can view this as the group theoretic version of Kahn's embedding problem, which is, the Kahn's embedding problem has been open since the 70s. Okay, so I would like to tell you a bit about measure theoretic Sofic entropy. The story is very similar. How do you define these invariants? But there's a different set of applications. Okay, so let's say that we have actions by measure-preserving transformations. Then we say that they're measurably conjugate if you have a measure space isomorphism which intertwines the actions. And we would like to classify these actions. And in particular, we would like to classify Bernoulli shifts. So a Bernoulli shift is just like the full shift, except that we put a product measure on it. Okay. So, if you like, you can just think of taking your group, you think of the Cayley graph and you think of flipping a coin at every vertex. That gives you a sample of the Bernoulli shift. So can we classify Bernoulli shifts up to measure conjugacy? You give me a group. For every k and every kappa, we have a Bernoulli shift. So that's an infinite dimensional space a priori. Can we say when two of these are measurably conjugate? It's a very basic problem that in fact inspired Kolmogorov to define entropy in dynamics back in 1958, 60 years ago. Okay. So this is the way that David Kerr and Hanfeng Li did it after I did it. But I like their definition better, so we'll do it that way. Okay, so let's say we have an action by homeomorphisms, just like before. And just like before, we're going to count pseudo-periodic orbits. But this time, we're going to require a little bit more. We're going to require that they are approximately equidistributed with respect to the given measure. So what does that mean? Well, if we have a map from a finite set into X, then we can just put the Dirac measure on the image of any point and just take the average. And we call that the empirical distribution. Okay, now if we have some open subset of, or open neighborhood of a fixed measure, mu, then we will say that a map is a good pseudo-periodic orbit with respect to all of these parameters. If it's a pseudo-periodic orbit in the topological sense mentioned before, and its empirical measure is close to the to the target measure, so it has to be in this open set. Okay, so we're just adding parameters. That's all that we have to do. We can now define the Sofic entropy of a measure-preserving system as the exponential rate of growth of the epsilon covering numbers of the pseudo-periodic orbits with all of these parameters. It looks difficult and complicated, but in fact it is computable in many cases. By the way, there is a variational principle, so the topological entropy is just the soup of the measure-theoretic entropies taken over all invariant measures. And measure Sofic entropy is a measure conjugacy invariant. In a way, it's not a difficult thing to prove. Once you think about The continuous case is the easiest case, and then in the measure theoretic case, you just approximate continuous maps by, you approximate measurable maps by continuous maps. Okay, it agrees with classical entropy in the amenable case. For Bernoulli shifts, we can compute the entropy completely. It's the Shannon entropy of the base, given by this formula. So in particular, the 2 shift has entropy log 2, the 4 shift has entropy log 4, just as you might expect. And so this answers the question of Ornstein and Weiss. Now, there's this question, can we classify Bernoulli shifts? Let's say that we have an infinite group. We would imagine that these 2 Bernoulli shifts are isomorphic if and only if their entropies are equal. They should be classified exactly by entropy. So in this direction, so suppose that we have 2 Bernoulli shifts that are isomorphic, then this was Kolmogorov's inspiration for defining entropy, is to solve this problem for Z. Then it was extended to amenable groups and now to Sofic groups. In the opposite case, Ornstein famously proved the converse for the integers in 1970. This was extended to arbitrary amenable groups. Stepan showed that you could do this whenever you have a group that contains the integers, and in fact, the proof is just like 1 or 2 lines. Because you see, once you have an isomorphism for the integers, you can build an isomorphism for gamma just by coset by coset. So it's a very, okay. So taking this idea of Stepan's and applying it to, using measured equivalence relations, I was able to extend it to all groups, but I had some technical restrictions, and recently Bannon Seward has removed these. So we in fact know the entire story now in this direction, but the other direction is still open for non-Sofic groups if they exist. Okay, so I would like to tell you a little bit about what's been going on in the last few years. So what I just told you was mostly, mostly 8 years ago. Okay, so I've been trying to classify Markov chains over free groups. This looks to be a very, very hard problem. By the way, Markov chains over the integers are classified up to measure conjugacy just by entropy, as long as they're mixing. It's easy to deal with the non-mixing case as well. But for the free group, this is no longer true. And in fact, it appears that there's an infinite dimensional space of Markov chains. And we need more invariance. But you can compute entropy in many cases. There's been a real explosion of work in algebraic dynamics. So when you have a group acting by automorphisms on a compact group, usually a compact abelian group, it turns out to be the most interesting case. There are many explicit formulas for Sofic entropy. Most of the, like for example, for principal algebraic actions, and there are a lot of nice structural results, for example, identifying the Pinsker algebra. And so these are a lot of the recent work is due to Ben Hayes, but it generalizes earlier work due to many people. Rockland entropy is a different kind of entropy theory that has been developed and introduced by Brandon Seward. It's something that can be defined for arbitrary countable groups, but it's very hard to compute unless you have Sofic entropy. It's an upper bound for Sofic entropy, but Sofic entropy is the only known lower bound for Rockland entropy, which means that if you don't have Sofic entropy, you can't bound it from below. But Brandon Seward, nonetheless, has used it to get generalizations of classical entropy theory theorems like Krieger's generator theorem and amazingly Sinai's factor theorem for all countable groups. So if you have positive entropy, Sofic or Rockland, then you factor onto a Bernoulli shift. So this is great. I mean, this is one of the first structural theorems that we have for arbitrary groups. Tim Austin recently posted a solution to the weak Pinsker problem. So this is showing that an arbitrary action of the integers, ergodic action, can be decomposed as a direct product of a Bernoulli shift and an action with entropy less than epsilon, where epsilon is pre-specified. And in fact, it generalizes to amenable groups. I've recently found a counterexample for free groups to the analogous question. And this counterexample, it uses statistical physics on random regular graphs. It develops new Sofic invariants that are similar to entropy theory. And it's a Markov chain, which just kind of indicates to you that Markov chains can be weird. Okay, I'm out of time, so thank you very much.
Thank you. Are there any questions, comments? Okay, apparently not. So in that case, let's thank the speaker again.